Hello, welcome to the lecture series on vehicle dynamics. In this session, let us discuss about squat and dive. In earlier classes, I explained what exactly we mean by squat. Whenever a vehicle is accelerated, the load from the front, the dynamic load from the front gets transferred to the rear so that the rear portion dips and the front portion lifts up. This is what we call it as squat. Squat is the dipping of a car's rear end that occurs during hard acceleration, we say. So it is caused by load transfer from the front to the rear suspension during acceleration. So dive is something like an opposite phenomena. It is dipping of the car's front end during braking. So again, dive is caused by load transfer from the rear to the front suspension during braking. So the now question is, because of the squat and dive, it leads to pitching of the vehicle. How exactly the suspension needs to be designed to reduce squat and dive phenomenon? Here, anyway, it is taking time. Yes, that is what. So using this video, we can just observe the squat and dive phenomenon. Okay, it's taking time. Anyway, we'll move forward. You see here, during acceleration, this is the load on the rear. This part is the static load with the usual conventions defined, and W into this is what you call it as the dynamic load. Okay, the second term on the right hand side of this equation is the weight transfer effect. The weight is transferred to the axle and wheels principally through the suspension. Therefore, there is an implied compression in the rear suspension, which in the case rear drive vehicles has been called power squat. Concurrently, there is an associate rebound in the front suspension. The combination of rear jounce, that is compression, front rebound, that is expansion, deflections produce vehicle pitch. So suspension system may be designed to counteract the weight transfer and minimize squatted pitch. So now let us introduce some kind of anti-squat. So we can generate anti-squat forces on a rear drive axle by choice of suspension geometry. So we can assume that all suspensions are functionally equivalent to a trailing arm. Trailing arm means Suppose you consider this is the frame and this is the wheel and this is the arm. We attach like this. This we call it as trailing arm. Suppose your wheel is here, front wheel. If we attach this, then this is leading arm. Okay, trailing arm. So all suspensions are functionally equivalent to a trailing arm with regard to the reaction of forces and moments onto the vehicle. So now I have just considered the rear wheel. These are the arms, upper and lower. If I just produce these lines, they meet at an imaginary reaction point. So this one. So from here to the reaction point, the distance is d. And the height of the reaction point is E. Now you see here about this reaction point, Fz into d. So this Fz into d, a counterclockwise moment. Correct? Then Fx, which will be here, the traction force. We are using, it comes into play when you are accelerating. This force about this point will create a counterclockwise moment. This is Fz into E. If I Fx into E. So Fx into E is equal to Fz into D. So Fz by Fx, it is going to be E by D. So this is what the equilibrium equation is. So now let us see where exactly this pivot point should be located. Correct. For that, let us say this, assume that d, this is at a distance d from here and this is at a height e from here. R is the radius of the wheel. Fx is the traction force. During acceleration, you are already having static load WRS, which is nothing but WB by L, which is the wheelbase length. To that, the dynamic load gets added up. That is nothing but, let me call it as delta WR, and that delta WR is nothing but W by G H by L AX. This is the reaction force. Correct. Now let us take moment about pivot A. WRS by D plus W by G H by L AX into D. Okay. These are the moments like this. Okay. Okay, fine. And let us take this moment. WRS by D minus delta WR by D. One thing. Also Fx E. Correct now? Fx into E clockwise. Because of this load, there is a clockwise. these two clockwise moments, this counterclockwise moment. We'll equate it to 0. Okay, right. You will get this equation. From this equation, we can find out what is delta WR. So you are getting delta WR is equal to this. And because of this, the rear suspension stiffness into rear suspension deflection. This becomes the stiffness force. This will resist this force. Okay. Similarly, in the front, what happens? It loses so much of load. And delta F will be the deflection of the front spring. And Kf is its stiffness. So now the question is, your vehicle will be like this. Let us say it will pitch like this. The front fellow stiff, this front suspension will get lifted up by delta F. The rear suspension gets compressed by delta R. And this length is L. And this angle is theta P. Okay, that is pitch angle. So we can say now delta R minus delta F. If you want, what you can do is we can draw like this. Okay. So now this will be delta R minus delta F by L will be the angle. Okay. Right, sir. So now from this equation we can obtain delta R. From this equation we can get delta F. Delta R and delta F value we can substitute. Finally, I'm going to get this equation. Correct? No. Now I want pitch to be 0. So I'll get this way, reorganizing. Put theta P is equal to 0 in this equation. Then finally, I get E by D value. So this is, you will get H by L. H by L, KR by KF you will get. And this will give you condition for anti-squat. Correct? This will tell you how much rear suspension should lift to compensate a rebound of the front suspension. Okay, this will give you that. So now what it means is that first part, if I plot, H by L is equal to E by D. So this is the wheelbase length. Let us say I'll just draw a line passing through the height of center of gravity. Let me mark that is H, and this is wheelbase length L. Let me join these 2 points by imaginary line. Okay, on that point, on that line, you select a point. You say E by D is equal to H by L. By similar triangle principle, E by D is equal to H by L you will get. So this trailing arm, what we are talking about, one end is fixed to the wheel. If I can fix it the other end on this, any point on this line, so that this equation satisfied E by D is equal to H by L, then we can achieve anti-squat. So you can say, you can call this arm as anti-squat arm. Correct? Anti-squat. So the anti-squat equation E by D is equal to H by L defines a locus of points extending from the tire contact point and the ground to the height of center of gravity over the front axle. So locating the trailing arm pivot at any point on this line will provide 100% anti-squat. Fine. Now by chance Kr is equal to Kf. So then our E by D will become approximately 2 H by L or H by L by 2. So now let me draw H and L by 2 from here. Then I can form a triangle. I can join these 2 points. Suppose I connect this arm to any point over here. Any point. It can be here, it can be here, anywhere. Correct? So now this equation gets satisfied. Then anti-pitch condition is satisfied. Then it is anti-pitch. Correct. Now if I have such role, you see here, if I can use linkages like this, these are trailing arms. These 2 bars will satisfy the anti-squat condition, and these bars will satisfy anti-pitch condition. So that way I can have this. Suppose I use only this, anti-squat is satisfied, but anti-pitch will not be satisfied. Suppose sometimes you can also think of introducing more stiffness, roll stiffness, then you can introduce an anti-roll bar also. Okay, this is how the suspension linkages will come into picture. Okay, right. So front solid drive axle. So that E by D is written as minus. Here you are using leading arm. So here what you can call it as the first term corresponds to the anti-lift on the front axle rather than anti-squat on the rear axle. The negative sign on the right hand side of the equation implies that the pivot must be behind the axle, corresponding to an effective leading arm arrangement to obtain anti-lift behavior. Right. If at all an independent suspension is considered, then we have to consider the radius of the wheel, then E minus R by D minus H by L. This is the kind of equation you get for independent suspension. Okay, so if at all you are braking, then the load gets transferred from the rear to the front. The vehicle dives. So that one is called power squat. This is called brake dive. So obviously then you have to have linkages which can resist dive. If I can do the similar analysis, I'll be getting something like EF by DF is equal to minus H by zeta L. Zeta, suppose it is 60 40. It is a fraction of the brake developed by this thing. Okay, 60% of the load is there, so zeta can be 0.6 like that. The same way, we have to have a rear suspension. This is the ratio. That means take height of center of gravity, take zeta L from here, maybe it is 0.6 of L. Okay, if it is 60-40, then you need to connect this arm on this line. So similarly this one for anti-dive. So many of the times we may not use so many linkages, so it is difficult to completely eliminate the anti-dive or anti-squat, right? Okay. To obtain 100% anti-dive on the front, 100% anti-lift on the rear, the pivot for the effective trailing arm must fall at the locus of points defined by the defined ratios. If pivots are located below the locus, less than 100% anti-dive will be obtained. If above the locus, the front will lift and the rear will squat during braking. In practice, 100% anti-dive is rarely used. The maximum anti-dive seldom exceeds 50%. Full anti-dive requires that the pivot be located above the point required for full anti-squat. Thus, acceleration lift would be produced on solid drive axles. So, flat stops are subjectively undesirable. With full anti-dive, front suspension caster angle changes may increase the steering effort substantially during braking. The required steering system geometry may be quite complex. Excessive variation in rotational speed can occur in the drivetrain as the wheels move in jounce and rebound, causing rattling and noise in the drive gears. Something like we are over constraining things. In the rear suspension, oversteer problems may be created by the high location of the pivot. That will definitely help in steering, making the vehicle oversteer. So this I'll explain in subsequent chapters. Brake hop may be induced if the effective trailing arm is too short. The propensity for brake hop is reduced by suspension design with a long effective arm. So it starts lifting up. So NVH performance may be compromised. So I think it is basically a judgment by the designer compromising all these things where exactly the pivot point has to be selected. Though the ideal locations have been defined, but meeting all the requirements may be a difficult issue. So we need to compromise, simulate the whole model, test it, and choose the right point. Okay, and right proportion. So that is what anti-squat and anti-dive suspension is. Okay, so you have seen these arms in the suspension help in anti-squat and anti-dive design, like resisting anti-squat and introducing anti-squat and anti-dive. Then between the arms we use the springs, and that will help in resisting roll moment. So while designing suspension system, it is necessary to consider all these issues and the linkages have to be designed. So when we take the real design, how exactly we consider all these things, we will discuss that. Okay, now thank you very much.